This is Jens Terhaar from University of Bern. And the short introduction that has been written by the Secretariat, and I didn't learn it by heart because it's better to read it. Jens is a biochemical modeler at the University of Bern. He is interested in high-latitude oceans and ocean climate interaction. He is currently an Ambizione Fellow and works providing more accurate projections of Arctic ocean ecosystem stresses such as ocean acidification. Is that approved?
Yeah, that's correct, yeah.
Is it correct? So we didn't miss anything?
No, that's correct, yeah. Perfect.
Father of three.
Yeah, that's in addition, yeah.
But I would like to add, before I let you loose, and that is that Jens this year was awarded a very prestigious prize by EGU, European Geophysics Union. Geoscience Union for early career scientists. But I will not read the argument from EGU loud, because then you either get so shy or so proud that you cannot focus on your presentation. It was a fantastic press release they had. But anyhow, Jens, your title is Atlantic Overturning Inferred from Air-Sea Heat Fluxes Indicates No Decline Since the 1960s. Please.
Thank you, Björn, for the nice introduction, and thank you, everyone, for giving me the opportunity to present my, or better say, our research here that I did partly in Woodsole and partly at the University of Bern. And I'm happy that you didn't read out the thing from the award because it's embarrassing. They exaggerated far too much to get me the award. So I don't want to hear that again. So you might be wondering why I'm working on the Atlantic overturning circulation, being an ocean biogeochemical modeler. And just want to say that's mainly due or thanks to the Climate Environmental Physics Division in Bern, because it's such a broad and interdisciplinary place where I could focus or work in very different places and very different topics. And it's thanks to the people there that I could do this. So let's dive into this. So what is actually the Atlantic overturning circulation? So we can look here at a nice animation. The Atlantic overturning circulation you can see in the North Atlantic. You have the water density as the surface, so it gets denser the colder the water gets that is transported northward. And then once it gets to the subpolar gyre, the south of Greenland, it starts to sink and then flows backwards into the other direction. So you can see how it goes down at different places in the Irminger Sea, Labrador Sea, and then basically flows down southward back to the Atlantic. And this looks pretty simple, but if we look in a bit more detail into this looks actually more like this. We have a very complex system of intertwined currents. We have the surface currents here in red. I think I put the pointer somewhere here. So we have those surface currents here in red. They go northward, and then there's sinking places in yellow, and the water goes then back along the coast, mainly back to the south. So why does the system matter? Because the whole system transports a lot of heat. So I think I can also point there. Well, no, I don't see this anymore. Yeah, it transports a lot of heat northward to the North Atlantic region, where it's lost to the atmosphere, and a bit is going to the Arctic. And it basically warms the atmosphere around over and around the North Atlantic. And here we can see what happens if the system wouldn't work anymore. So these are projections of sea ice under moderate emission scenarios, so somewhere between high and low emissions. And we can also end with an AMOC collapse that was induced by freshwater being put into the North Atlantic. So this is the sea ice extent in February, and there are a couple of things that you can see. So you would be able to walk basically from Norway to Greenland to Canada, and it would get really cold even in Denmark and Germany and the UK. And to see how cold it would get in such a scenario, these would be temperatures that you could expect every 10 years in winter in Europe if the AMOC would collapse. So I think this shows very nicely that it's extremely important to understand the system and how it's working, and if it's in danger of breaking down or collapsing. So how do we know how the circulation works? Because as you can see, the North Atlantic is a really big ocean basin, and it's hard to observe water flowing northward there, and it's a lot of water flowing northward. So there are moorings that were installed at different places. So you see them here in yellow, where temperature and salinity are measured, and then you can calculate density and the geostrophic currents. And you need to measure the Gulf Stream, which is only a small but important part of the overturning circulation. And based on this, we can measure the currents that flow northward and southward. And this looks like this. So there are a lot of colors in this plot. And the different parts of the system. So the Gulf Stream in blue flows largely northward, transport a lot of sware drips. So it's basically the amount of water flowing northward. And then in green is everything that's done by wind close to the surface. In purple is what's going back south. And the net transport then is a red line there. And the question arises if it has gone down. And based on these observations that we have since 2004, we can't say if the system has gone down or not. There might be a slight decline at the beginning, then it increases a bit again, but the time series is just too short, given the overall variability in the system, to really say if there's a long-term trend yet or not. So given that we can't really say that, but we are still interested if it has changed over the past, we need different ways to understand how the AMOC has changed. And most of these are based on proxies, and they use then the idea of physical concepts. So as I said before, the AMOC transports heat northward. So if it reduces, we would expect less heat going northward, less heat going to the Arctic, and less heat being lost to the atmosphere. And the easiest way to observe this, what was used as a long time for a proxy, is to look at the temperatures in the North Atlantic, because we would expect then, if the AMOC reduces, that it gets colder. So this is one of the most used proxies. We have it's called the cold blob, or it's often called the cold blob. So the idea is that we look in the temperatures in the subpolar North Atlantic, see how these temperatures change compared to the global warming signal that we have. And if these temperatures warm less or are colder than the rest of the globe, then we would expect the AMOC that was the idea that the AMOC has slowed down. So this was done by Caesar et al. and Rahmstorff and different people before. So what they did, they calculated this AMOC index, again, they're on the left side, and plotted it against the AMOC anomaly, and then used a couple of models this is CMIP5, so not the last or the most recent generation of climate models, but the one before. And they looked at the trend over the entire century. So how much has the AMOC changed over a century, and how much has the AMOC index, so the SSTs compared to the global SSTs, changed? And you see they find a really nice relationship. And the gray models are the ones that don't represent the historical AMOC well in their simulations, so they excluded them from the fit. And based on this relationship, they can then deduce as the blue line, just forget about the red line, we don't need this in this graph. So they can make the blue line, which is a reconstruction of the AMOC since the beginning or end of the 19th century. And we can see that we see a decline around the 1950s, 60s, then it recovers a bit, and then it declines again in the last 20 years approximately. So this proxy suggests that this has happened. So what we did in our study then, so now it comes a bit to our work, we repeated the analysis. We just wanted to see if it works with the newest model generation. And this is what we get. So each dot is again a model. And then we did the linear fit for the same thing as I did. So we calibrated the relationship. And our linear fit is much less good than the one they found. So we have an R squared of 0.5, before it was higher than 0.8. And also, if you compare it to their fit, you get this line. So the calibration from CMIP5 models looks very different than the calibration from CMIP6 models. And then when you use observations of the change in the subpolar gyre SST, so the AMOC index, the gray line here, and you see where they intersect with the calibrated lines. You see that Caesar and Rahmstorff basically deduced from their calibration, with the models they had at hand at the time, a reduction of 1.7 square drops in the AMOC, and over the last century. If we use the most recent generation of climate models, we find a reduction of minus 0.2, but with an uncertainty of plus minus 0.7. So it's not a significant change that we can deduce based on this method and this proxy. So now I just want to give you a brief history, because we are by far not the first people who looked at this. So this was the first study that did this. They used just one model and looked at decadal values and found the high relationship between the AMOC index and the AMOC. Then there was the multi-model analysis from Caesar. And then there came other studies. There's Olsen et al. They used a different set of CMIP5 models than Rahmstorff and Caesar used. And they come up with a much lower relationship. Then there's Minari et al. And I think this is the most conclusive study in terms of simulations that they used. So you see they used around, how much is it, 64 models in total from both generations. And what you can see here is that the relationship that looked on first hand like a very neat and clear relationship, it exists, but it's much more uncertain than we would like it to be. So it's very hard now to say, given on a special change in SSTs, to really deduce a change in the AMOC with a high uncertainty. And this is basically the same that we find. We find the relationship exists, but it's almost impossible by now to really exploit it, to learn something about the AMOC. So given, let's say, and something else, I think one reason why it doesn't work is I think they look at trends over long time scales. And I think trends in general over centuries, given the variability in the system, are not very well suited to understand the real change. So here you can see for one model, a change in the AMOC over the last 170 years. And if you make the trend line through it, it looks, if you only look at the trend, you would say it has increased quite a lot. If you look at the real time series, you actually see it's just a low variability at the beginning and then a high at the end. And that leads to a seemingly increase in the AMOC while it's only varying around a mean value. And similarly here for other models. So the trend might suggest an increase or a decrease while it's not actually increasing or decreasing, just depending where the phases of the natural variability are lying. And just as an example, the model that doesn't really have a trend, if you look at the blue line, it's just stable and moving around there, is the one that shows the highest trend here. So it would suggest that it has increased, but it doesn't really. So I also believe that the trend is not something to look at. So we then also try to see if the trend isn't maybe the best metric. Can we just look at annual values? So in 1 year, we look at the AMOC and the AMOC index, and how does that work? And then we come up with this. So you have the SST anomaly in the subpolygia, so the AMOC index against the AMOC. And you can see on annual values, it just doesn't work at all. I mean, there's an R-squared of 0.15. There is a relationship, but it's not nearly good enough to deduce anything. Then we went to decaded average and thought that must be working. And we got this. It gets a bit better, 0.3, but still not good enough to really deduce with a low uncertainty the AMOC. And on overall, so this would be on centennial scales, it gets worse again. So this is what we found, and then we thought, okay, this apparently does the idea is right, but this doesn't work good enough to use it. And so we went back to the drawing board and thought about the heat budget again, and looked in the models at the different parts of the heat budget. So what goes north, what goes out to the atmosphere, what stays in the ocean, heats the ocean, what goes out to the Arctic. And we did that in a lot of different models, and I just put them here all on the left side. For 18 models, we had all the different components. And then all the plots look like the one here on the right side. So you see the northward heat flux anomaly into the Atlantic, so basically what's driven by the AMOC in green, and the heat content change in blue, what goes to the Arctic in gray, and what goes out to the atmosphere in orange. And you can see when there are changes in the AMOC, so the heat transport anomaly northward, they're mainly compensated by changes in the air-sea heat flux. So we wouldn't expect to see the signal from the AMOC actually in the SSTs. We would rather expect it to see it in the air-sea heat flux. And so if more heat goes northward, made this here in a nice simple box plot. So we have the heat going into the Arctic, heat content change, air-sea heat flux, and going to what goes into the Arctic. And if we change this, so if the AMOC gets stronger, there's more going into the North Atlantic. It's actually mostly lost to the atmosphere, and vice versa. If it gets lower, there's less going out to the atmosphere. So the tracer or the proxy that we actually have to look at is the air-sea heat flux, because that is more strongly related to the AMOC than the change in the ocean itself. And we just looked at this in the scatter plots to make sure that this really works. So this time it's 24 models for which we had the output. And here you see the meridional heat transport anomaly against the North Atlantic air-sea heat flux. And we also don't find a good relationship on annual timescales. There's just a lot of noise on small timescales that doesn't allow to do the annual reconstruction. But on decadal timescales, it works very well, and on centennial timescales, even better. And then this is not yet the AMOC. To get the AMOC, we have to relate the meridional heat transport anomaly to the AMOC anomaly. But that works extremely well because what flows north, the amount of heat doesn't really depend on small temperature changes. It depends really on the large-scale volume changes of water that flow northward. So we expected this to work. And now we can combine this because these two axes are the same thing. So we move the two relationships together, and we come up with this relationship where we have the AMOC anomaly against the North Atlantic air-sea heat flux anomaly. And there you see that all these models, and we can do the same thing with CMAP5 models. I didn't put this here. It looks exactly the same. give this relationship between the North Atlantic as a heat flux and the AMOC. Now that we have this, we can use it. We can use estimates of the North Atlantic as a heat flux anomaly, and we can deduce the AMOC. And we did this in models. So we took out one model of this calibration, used the RC heat flux anomaly of the model, and reconstructed the AMOC. And I just want to show you how well that works. So this is the MPI Earth System model from Hamburg, and they simulated the AMOC. And now we used the RC heat fluxes from that model and the relationship that we just calibrated, and we come up with this reconstructed AMOC without knowing the actual simulated one. And if you put them on top of each other, you can see that this works very well. It's a 2 sigma uncertainty range, and we can actually say something about how the AMOC has changed with a relatively high certainty, not uncertainty, with a low uncertainty. And so here you can see that for a lot of different models, we made the test for each one of them, and most of the variability and trends are captured very well, as you can see. But I also want to highlight things where it doesn't work anymore. So we have these places here, where you can see that the directly simulated AMOC is higher than the reconstructed AMOC. And this happens towards the end of or to the beginning of the 21st century, and only in models with a high ECS, with a high equilibrium climate sensitivity, meaning models that warm very fast and have warmed faster than we have observed in the real world. So in these models, what is actually happening with our relationship is that in addition to the 4 fluxes that we looked at, we get an additional 5th flux, that is the global warming signal that leads to additional warming, but without changing the marine heat transport and the AMOC. So we get this additional heat flux in there that is not related to the AMOC. And what happens then to our relationship is that the heat flux increases. So it moves to the right without the AMOC. But what we deduce from this heat flux is this other star. So we deduce an AMOC that is much lower than the actual AMOC that is there. That's a problem, but only on a one-sided problem, because the climate change is only leading to warming and not to cooling. So our approach can only overestimate the AMOC or underestimate the decline. We can't overestimate the decline because of this effect. So when we do our reconstructions, we might underestimate the decline, but we will never overestimate it based on this caveat. So this is what happens here. And so the directly simulated AMOC is actually higher than the reconstruction. And then we reconstructed it. So this is now our reconstruction based on observation-based RC heat fluxes from reanalysis data, from a European one, ERA 5, and a Japanese one. And you can see here the reconstruction over the last 60 years. It's decadal averages, because we can't do annual averages. And the uncertainties are plus minus 1 standard deviation, and only the uncertainties from the calibration. There's no direct uncertainty from the reanalysis data. And what you can see also, they agree the time series within plus minus 2 sigma. There's a little bit more uncertainty at the beginning, which within 1 sigma can definitely happen. And it gets closer at the end because we have just more satellite data to constrain the reanalysis products. And the total uncertainty, I would estimate that as the difference between the 2 products to add that together. And what we also see that we have a slight positive trend in these. It's not significant, but it's the RC heat fluxes definitely suggest that there's no decline yet in the AMOC. So this is the most important result that I want you to take home from this. And the advantage of our approach is not only that the calibration works much better, that it's more on a process-based understanding of what's happening with the heat in the North Atlantic. It's also that we can just reconstruct the AMOC wherever we want, because we just use a box and put the budget calculate the budget of the box. So we can define the box as we want. We can just move it forward. So say we don't want to know what the AMOC is at the rapid array at 26.5 degrees. We want to know what it is at 30 degrees. So we just make the box smaller and look at the RC heat flux north of that latitude. We can do that for any latitude, so go to 35, and then look only at the RC heat flux anomaly north of 35 or at 40 degrees. So that allows us to be much more flexible with the SSTs. They were only related to the 26.5 degrees north. And what we find then is the different reconstruction here, again, for the 2 products, for each of them. And one thing that I found was interesting when I looked at these reconstructions, there's no decline at any of these latitudes yet, which doesn't mean, but obviously it will start to decline at one point. That's just the physics when it gets warmer and fresher in the water. But so far it hasn't happened. And also, if you look between 35 and 40 degrees, there seems to be a bit of a change. So the reconstruction south of 35 is not really strongly related to the one at 55. So that's approximately the border between the subtropical and subpolar gyre. So this is also something that's known for a long time, but for a lot of people not really intuitive, because we always think of it like in the animation that I showed at the beginning, it's just flowing north, going down and south. It's a much more complex system. So the AMOC at 26 is not necessarily the same as the AMOC at 40 or 55 degrees north. And since we published this, we worked a little bit more on this, and I just want to give you now a bit of an insight on what we have done since, because I find this very interesting and potential to make it even better. So I said we can't do the annual reconstruction when we only use RC heat flux anomalies and AMOC anomalies. We now added other parts of the budget, which are smaller, but still useful. So we added the ocean heat content change on the x-axis. So we look how the ocean heat content and the RC heat flux change and how that relates to the AMOC. And actually the ocean heat content change, that explains a large part of the uncertainty on the annual average values. So we get a much better relationship on the annual average values, and an even better one for decadal and centennial. So if we could observe, and I think with the Argo floats we are there now to do this, if we can really use the ocean heat content change year by year and the RC heat flux anomaly to even better reconstruct the AMOC then, or even use it as a way not to observe, but an indirect way of looking how the AMOC is changing in the future. So each year, if we know these two variables, we have a fairly good idea what happened to the AMOC without really having to observe it. Having said this, I don't want to use this as a replacement for observations. Direct observations are extremely important, and no proxy will ever replace this. So I don't want to be misunderstood and misinterpreted that I say we don't need the observations, but I think it's a nice additional tool, especially because we can move it to different latitudes. So then, if we know the RC heat flux anomaly well and the ocean heat content change, we can really have a good idea of the AMOC at different values. And the other advantage is if we do the ocean heat content change, we get rid of the climate change problem, the warming problem, because this additional part is then in there. So here you can look at you see the relationship in the future for a low and high emission scenario. And with the additional warming, what we would have expected is that the whole thing moves to the right. As I showed you before, if we get the warming in there, then we get an additional heat flux that doesn't manifest itself in a change in the AMOC. But if we account for this additional ocean heat content change and take it off again, we move it back to the left, and then we can actually really reconstruct the AMOC also in the future based on this proxy and over the entire 21st century. And the relationship is stable, so it's really, I think, a nice tool to think about how we can add this to our understanding of the AMOC and how we can use it as a tool to look at different latitudes relatively cheaply compared to putting arrays everywhere and moorings everywhere. So this was a lot of positive things, and I think I have some time, so I would like to talk a bit about a few of the caveats of the study, because it all sounds very convincing and very good. But of course, as always in science, it's not everything is working 100% well as we want to. So what we did is we reconstructed the AMOC based on RC heat fluxes. But here I want to show you what RC heat flux reconstructions, if you integrate them globally, so not just in the North Atlantic, how they work. So we have the ERA 5 that we use is the green line, and the JRA is the red line. And you see the two similar lines there, they're the actual ocean heat content changes globally. So we see that this reanalysis data that is based on observations from the atmosphere, they either overestimate the heat that goes into the ocean by a large amount, or they underestimate it, but they're not close to the actual heat that goes into the ocean. So there's the large question, how reliable are these estimates of the RC heat flux really, if they can't reproduce the global integrated heat flux into the ocean by quite a large amount. And now I want to show you why I think for our problem, or for our study, we can use them. Because if you look at the regional distribution of these fluxes, so these are the adjustments that would be needed so that these lines don't overestimate or underestimate anymore. So what these colors means, if one product has a blue color, it overestimates the flux quite a lot in this region, and if it has a red color, it underestimates the flux. And I want you to focus on the North Atlantic, that is on the upper right corner there, with the nice lines indicated there. And in ERA 5, the adjustment that is needed, or the difference, is relatively small. In JRA, it's a bit higher. And then there's another product, Core V2, where the adjustment that is needed or the error in the North Atlantic is almost non-existent. We didn't include this in our study because the time series from this data stopped in 2007, so we didn't have it for the entire time series. But now I just want to show you how it looks like if we add this, because this is supposedly the best product in the North Atlantic. And this is if we add it to our reconstruction. It's the green line that came on top of it. And you can see that it's not significantly different from the reconstruction that we use, which makes me believe that, given that it's a third product, one that works very well in the North Atlantic, that they all agree more or less on the tendencies there than the uncertainties, and none of them shows a decline that we can trust them to the extent that it's necessary to use it for the reconstruction. And also, we made the same thing for each latitude, and the whole structure at each latitude looks very similar, which also gives me confidence that these products can really be used for this. Of course, we have to keep in mind that there are uncertainties, but what we can see from this that we so far can't infer using this technique a reduction in the AMOC. And just one last piece to it, we did the same thing with salinity. So that was something that Thomas suggested to me after we published this. Why didn't you look at salinity? Because if the AMOC reduces, it transports a lot amount of salt northward, then there should be less salt in the North Atlantic. And the advantage of using salt, then we can use it inside the ocean because it doesn't evaporate or it doesn't go out like heat. There's not such a large flux. And we did the reconstruction, so we calibrated. I don't want to show you everything here. This is just the result. We calibrated the AMOC against the salinity anomaly. It works fairly well. The uncertainties are a bit larger because the relationship is not that strong. It's 0.6 for the R-squared. But we come up with this reconstruction then for two salinity products. And if we put this then next to our AMOC reconstruction, now also extended a bit further in time until 1940, we see that the general evolution, so the signal is a bit damped in the salinity. I don't know yet why, but the general idea is the same thing. We have this slight increase around the 1960s that we can see here, 1960s, 70s. It decreased towards between the 1970s, 80s, and increase again at the beginning of the 21st century, and then a kind of stabilization. So I think this is hopefully going to be something, it's yet unpublished, but I hope that we can find the time to publish this in the future. And I think, I hope that I could convince you that based on all these different reconstructions, I think that we can't yet infer a reduction in the AMOC. So to sum up the take-home messages, I think sea surface temperatures in the North Atlantic, they are related to the AMOC, but the relationship between the AMOC and the sea surface temperatures is just not good enough to use it as a proxy for the AMOC with the uncertainties we would like to have. Instead, RC heat flux anomalies allow reconstructing the AMOC and decadal and centennial timescales at various latitudes. If we also add ocean heat content change, then we can even do it at annual timescales. And based on this, the AMOC appears to be more stable and potentially also more stable to external forcing than previously thought. And this is basically turning around the discussion, because before we thought the models are not sensitive enough. Here, the reconstruction shows a lower sensitivity than we get in the models. So it might be that the future decline is also not as strong as we thought it will be. And I don't want to say it's not going to be very bad. It's going to decline, and it's going to decline strongly, and no matter what emission scenario we will use. That's what the simulations of all these models show us. But I just want to say a collapse might be not yet on the horizon for the 21st century. Of course, it can never be excluded, and just a small uncertainty should be more than enough to act as strong as we can to avoid this, because the impacts would just be horrendous, especially for us in Europe, for agriculture and everything that is related to our way of living. But I also think it's a good message that we might have slightly bit more time than we thought we have. And then in the future, I think this can provide a relatively cheap way to detect AMOC changes, complementary to real observations, which we always need and which are always more certain and better than just proxies of the AMOC. Thank you very much.